Hello and welcome. This is G, and this video is devoted to the Electrostatic-Sandbox SDK, and this will be the first video in this series, right? So first of all, we need to define some terminology, and this will be our agenda or our outliner, right? So the first thing first, the introduction and the terminology, and then we will get a glance over the overview of the software specification for the Electrostatic Sandbox SDK. This board over here, and you can find it on GitHub too, right? So then we will get a glance over the required skills to get you started developing for the Electrostatic Sandbox SDK. Then we glance over the README, glance over the build architecture and the build components, glance over the source code on GitHub, and then we will start getting hands dirty or hands with using Android Studio. Well, Android Studio is a recommended IDE, right? Not because we will use Android tools now, but because Android Studio enables the Clang D as well as the Java by default. So I can't recall exactly if the IntelliJ IDEA interface works the same as the Android Studio interface. I can't remember, but Android Studio is based on the IntelliJ IDEA, so you can test this and let me know. You can test this and let me know, right? Because I don't have much time to test the IntelliJ IDEA on the project, but it's much the same. So and if you don't have Android Studio or you don't want to use Android Studio, you could use any IDE. It's not a big deal. This the project is all based on a scripting, so there is a build architecture as well as a software architecture. So I don't know if we could actually take a glance over the build architecture as well as the software architecture too, but I hope this video will not be lengthy. All right, so let's get started fast. And you need to check first, yes, everything is running fine. Okay, this is an overview for the software architecture. Right, so first of all, I need to define the terminology. All right, the Electrostatic Sandbox SDK is a complete work-in-progress software development kit suite written purely in C with Java bindings, with a stock Java bindings, and it's designed to build distributed simulation systems, right? Together with an interface for distributed simulation systems, the IEEE 1516 HLA for high-level architecture. That's a specification written and developed by the Institute of Electrical Engineers and Electronics. All right, and it has the tag IEEE 1516, designed specifically for distributed simulation systems. So it's an API without an actual code, right? It's just an interface or a prototypical functions or prototypical code without an actual compilation or compilable units. All right, so this is IEEE 1516, so it lacks the RTI, the runtime infrastructure, and we need to develop this, and this will be incorporated into the one here, the simulation infrastructure here. Right, we will go over the different types of infrastructures that we have in this project, because we have like 3 sub-projects inside the main projects, and it might be like 4 or yes, for infrastructure projects, because the third Electro-IO is distributed into the Electro-MIO for microcontroller and Electro-CIO for the kernel IO, right? So first of all, let's continue with the definition. There is still more, right? So we said that the Electrostatic-Sandbox SDK is designed to build distributed simulation systems, as well as that there are insights from the NASA DSES. What is NASA DSES? NASA DSES is the National Aeronautics and Space Administration Distributed Space Exploration Simulation System. That's the DSES part, right? This system is based on the IEEE 1516 as well, and it basically, what it does is it attains the connection between distributed centers of the NASA. So for example, the Johnson Space Center, the Glenn Research Laboratory, the what else, the Marshall Space Center. Those all you can all those are distributed over the United States. You could connect them through the through this distributed system. So this is a distributed system, and it has a component for simulation, right? So now we got to a deeply technical point, which is what is the difference between a distributed system and a distributed simulation system. Well, both are distributed systems, but a distributed simulation is a much larger thing, because you add a component of the hardware. So you add the hardware to the distributed systems, and not only this, but also you add a component for simulation. So you don't do real stuff. If you have real stuff like rocket launching, for example, or you wanted to operate a surgery, for example, but you don't want really to operate it because it has complications. It might have adverse effects, and it might have failure routines. So you want to simulate these failure routines, these adverse effects, and the normal circumstances. You want to simulate all kinds of this stuff. So you could actually technically say that distributed simulation system are distributed system, but simulated for a specific kind of circumstances, all right? And it uses hardware as well as it could use software. So a point that I need to clarify, that distributed system plus hardware or software, right, plus a desire to simulate adverse effects or simulate failure routines or simulate normal circumstances. So you select what circumstances or what events you want to simulate, is equal to the distributed simulation systems. That's the equation we have, right? That's the difference between the distributed systems, and the major difference or the root difference between the distributed systems and the distributed simulation systems, right? So the major difference or the root difference is that we add the component of the simulation, which simulates the events of the system. It selects the events of the system to simulate it, and those events could be sometimes that they cannot be tested. They cannot be tested in real life, right? And if they tested in the real life, they will need preparations, pre-testing, and a very long time before launching the actual project or the actual runtime. All right, so we will have another video about this. Don't worry.
the distributed simulation and the GNU Linux and Java C. These are the keywords. The Java C 20. This is not an infrastructure. This is a binding API. This is a binding. This is for the binding APIs. All right. And it's for also the migrated projects. My old migrated, I migrated most of my, or almost all of my projects to the Electrostatic-Sandbox SDK to gain benefit from the native libraries that I'm developing for there. The the Gradle is a selective build system for this, right? And the ISO C99 was GNU extensions. This is the main programming language that we use. Embedded system design, first order and logistics, that will be omitted for now, and scientific modeling this here, right? So first we have a hierarchical patterns. We have like 3 infrastructures. A simulation infrastructure, that is the top, and that is recommended to build the systems. So the SDK is not actually the system. Let me remind you, this is not actually a distributed system or a distributed simulation system. It is a collection of tools that you could use to build your system, right? So for example, smart homes, for example, smart hospitals, for example, projects like the NASA DSES, all right? A couple of things, a lot. Well, you can glance over them on GitHub, all right? So simulation infrastructure, software networking infrastructure, and finally the hardware infrastructure. We get to the simulation infrastructure first. That is the interfaces of the IEEE HLA and the RTI, the runtime infrastructure. And it gets composed of federates, that's the devices that you want to connect it together. The FOM, the Federation Object Model, that's a standardization for the data structures to transfer or to encode from device to device, to encode in the transmission protocol, all right? And that is the federations, which is the RTI. So the host starts the federation or the RTI, and the other devices connect to this RTI and initialize, and connection starts, and then transmission starts by FOM. Transmission protocols are abstracted over the software infrastructure and are concretized over their infrastructures. So if you are running, for example, the IEEE 1516 on an AVR, then you will use this infrastructure here, the Electro-MIO, alright? But if you are running the same IEEE 1516 but on the AAR 60 or not AAR, let's say you're running this on an x86 64 Linux machine, it will use this infrastructure here, the Electro-KIO, this one here, all right? Which actually adds the uses the kernel user space APIs, right? So there is a difference. Now we get to another thing. We are not building kernel modules into this, right? Because that is a lot of work, and there is a difference between the user space and the kernel space. The allocation is quite different between both, right? So what we will use is basically the kernel user space APIs. So basically the IOCTL APIs, right? The IO control APIs that will control the driver created by the kernel module for a specific hardware through the file systems, right? So there is a connection channels. There are connection channels between the well, in this case it's only single connection channel between the the actual driver that is the kernel module has created for us according to the device, and the actual devices through the file systems, right? So in any ways we will get into these. Each one of these infrastructures will have a video, the names, the project has names, so they are subdivided into the whole project is subdivided into 3 projects here. So I have the ElectroSim, that's scheduled for 2026 to 2028. not relevant for now. The Electronet Soft, that's held for 2024 to 2026, that's a relevant one. And the hardware infrastructure, that's held for also 2024 to 2026, because this is the infrastructure that we will use. So the software and networking infrastructure will include standard libraries, process control, thread control, memory control, sockets, abstract file systems, electromass and logger utilities, and unit testing. This is very cool. All right. The next one is will depend on the style that not the style, will depend on the infrastructure that we will use. So the Electrum IO for the microcontroller, for example, the UART, Universal Asynchronous Receiver Transmitter, GPIO, General Purpose Input Output, SBI, Serial Prefer Interface, TWI for two-wire interface, and ADC for Analog Digital Converter, PWM for buswidth modulation, and other extension libraries. Now, the rest for this actually I need to just give you a note, right? This is formally known as Shaft AVR. So there is a project on the Electrostatic Lab, my organization, that is named, that has the name Shaft AVR. This will be abandoned, and the interfaces will be transferred to Electrum IO, right? So this is not maintained anymore. This will be archived. All right. There is a first order logistics here, but is not very relevant for now. But it shows some relations. Those relations. So those are superimposed and not juxtaposed. They are superimposed, which means that we get from this to this one, and we can get from this to this one. All components from this one can relate to this one. All components from this one can also relate with this one. So it's like a physical product set. All right. So the point is that we don't want to relate this to this directly, right? So no relations between this one and this one, because this is an abstraction. This is an infrastructure. So we want to relate the infrastructure to the software and networking infrastructure, right? And create a middleware here, and then build the relation between this and this one. That's far better than building this, because this would be a superimposed relationship, which means that all the components here will be related to those, or a specific component is in these, and not all. For example, those could be related to the abstract file systems here, this one here, right? But they couldn't be related for electromass, for example. We couldn't relate these all for electromass, right? We will get into details of these and the difference between juxtapose and superimpose, because that's an ontology, right? So, to not making everything lengthy, let's start first by running the Android Studio. Clear this. And during the running procedure and the initialization, we could go over just to check for this. Verify. Great. Let's go over the actual repository and show you some of the gems that we have. Right. So as you can see here, the Electrostatic-Sandbox SDK is a complete work in progress software development suite written purely in C. I will say this project is very neat, the NASA thesis, and you can read more about this. I have links into in this GitHub, and you can find the GitHub in the description box. All right. So this is the same architecture that we have. You should know that these are the migrated APIs. They are omitted from the board that we have displayed, the overview board, and these the migrated APIs and frameworks that we have serial 4J, Jector, Articular ES, Jimmy, Alloc, JSNAP loader, Automata 4J. We haven't yet migrated all of these, just except the serial 4J, and it's running fine, and it also links with the Electrostatic-Sandbox library. So all the APIs of the Electrostatic-Sandbox is now capable of being used by serial 4J. We're capable of providing permissions for serial 4J over the Electrostatic-Sandbox APIs, right? And about the sandboxing, by the way, this is not yet designed. So the federation, the IEEE-1516 runtime infrastructure will include federations, and those federations should actually be the runtime infrastructure that the host initializes, right? This part is the sandboxing, but it's not yet designed, right? Sandbox means that isolation. It should isolate this system from other systems running the same infrastructure, right? And they could all like run on the same server, and we haven't yet figured out how to do this, but in the meanwhile, this is the base that I want to get right now. The detailed architecture, and then the milestones. This is a very important. The tight period is between 2024 to 2025 or to 2026. That's a proof of concept. We wanted to provide the Electro IO, want to provide it for PIC microcontrollers, and we wanted to provide prototype simulation project and testing. And meanwhile, in the tight period, we want to find a primer or a primer version. The electrostatic primer is the frontier for our project. So the frontier means that whenever I want to add an API for the first time, I will first integrate it into the electrostatic primer. So we have two libraries, the Electrostatic-Sandbox and the Electrostatic-Sandbox primer. So technically electrostatic and electrostatic primer. So the script selects, you could select from both either the electrostatic core libraries or the electrostatic primer. The electrostatic primer have the early released or the early testable libraries. Those early libraries that we want to test for when they work fine, we could integrate them back into the electrostatic. This is like the MVP or the minimal viable product, but in a different fashion, and it uses like code directly. It doesn't depend on a specific architecture, right? And then the migration of supported project is the ElectroNetSoft and the Electro IO, and this would be the tight period. And then we have the proof of concept and the production period, right? The production period, that should we have the mature ElectroNetSoft, a mature software and networking infrastructure. That's the stable version. So stable version 1 will not include the simulation, the simulation infrastructure. All right. Another production period will include the base IEEE-1516. That's the ElectroSim project, and that will be a stable version 2. So starting from version 2, you could build fully fledged systems. That should be the vision for now, and those are all provisional. Then we have an open period. If you want to start from this, by the way, for testing, prototyping, and publications, that will be the very prosperity period, I think. All right, so these are the rest for the migration milestones. We have only migrated the serial 4J for now, and we are working on the Shift VR. Then the primer version will include the ElectroNetSoft and Electro IO projects only. So just like the OpenGDK, I have a couple of projects working on, for example, the Jigsaw project for the Java modules, the Amber project, the Banana project for the new native interfaces, and the one that I can't that I can recall its name for the virtual threads, for example. We have the same concept here. Multiple projects for different things, right? Each project is entailed for a specific reason. Now, those you could read this, and then the challenges, they're building the appropriate HAL on top of the low level. So we have a HAL. A HAL is a hardware abstraction layer. It's technically a software hardware abstraction layer. You can read this as a type of software hierarchical architectural design that provides generic application programming interfaces for the system as abstractions with replaceable infrastructure. So the idea is that we will have a replaceable infrastructure, and that's the vision, that we can actually replace the infrastructure, use the AVR or PIC infrastructure, use the Linux kernel, user space APIs, or the AVR infrastructures, depending on the system or the platform you are running. But at the same time, we maintain the high level architecture, the IEEE 1516 and the software and networking infrastructures, right? So this is a project. I will go now over the files of the project. This is the project. We go over the source code. So you can find the source code and the glancing over the source code in another video, because this is getting too lengthy. Alright, I will create another video with the glancing over the source code, and we want to make links between the source code and the actual architecture that I have just described. Alright, thank you, and until next time, I see you in the next video for the source code glance and hands on. Thank you.